I'm betting most of you have experimented with food coloring and water with your students to explore the properties of water as a solvent, or maybe even to demonstrate diffusion. Today we're going to take it to the next level as we attempt to make tie-dye milk. In order to conduct the tie-dye milk experiment, you'll need a few simple items, some whole milk, and a variety of colors of food coloring. To begin, add 1 drop of each food coloring dye to your whole milk. Try to make sure that you add the dye so that they do not mix immediately. You'll notice as you add the drops of food coloring that the dyes will react differently to the milk. Some dyes, such as the blue and green, may start to diffuse immediately, while other dyes, such as the yellow, will appear to stay in one place. This is an interesting point to discuss with your students and have them come up with hypotheses as to why the different food coloring dyes may react differently with milk. Let's fast forward and watch our dyes as they diffuse in the milk over the next several minutes. You'll want to have your students observe the dyes not only from the top but also from the side. They may notice that the dyes appear to be staying on the surface of the milk. Now we're ready for the next step in our experiment. For this step we'll be using regular dish detergent. You'll just need a few drops. Carefully add 1 to 2 drops to the center of your food coloring into your milk dish and watch what happens. Let's rewind and watch this in slow motion. As the dish detergent is added, the food dye molecules are immediately pushed to the edges of the milk. If we continue watching over the next several minutes, we'll see that the food dye molecules continue to swirl and move through the dish of milk. Eventually, this movement will begin to slow and come to an equilibrium. So how do we explain what's happening between the milk, the dye, and the detergent molecules in this tie-dye milk experiment? Let's clean up and take a look at the chemistry. So how do we explain what we observed in the tie-dye milk experiment? Let's take a closer look at the chemistry of these molecules to see if we can understand what happened. The first material that we used in our experiment was milk, whole milk. Whole milk is mostly made of water, but also contains vitamins, minerals, proteins, and tiny droplets of fat suspended in solution. The most common fat found in milk is a triglyceride, shown here. These molecules are highly nonpolar and are sensitive to changes in the surrounding solution, the milk. The second material that we used in our experiment were food coloring or dyes. These dye molecules are largely polar molecules that dissolve easily in water, the solution in which they're suspended. The secret of the bursting colors in the tie-dye milk experiment is that teeny drop of dish detergent. Dish detergent, such as sodium lauryl sulfate, is bipolar in nature. That means that one end, the hydrocarbon tail, is nonpolar, and the other end, the anionic head, is polar. Because of the nonpolar and polar regions, it weakens the chemical bonds that hold the proteins and fats in the milk solution. The soap's polar, or hydrophilic, water-loving end dissolves in the water, and its hydrophobic, water-fearing end attaches to the fat globule in the milk. This is when the fun begins. When dish detergent is added to the milk, things begin to move. Dish detergent weakens the milk's bonds by attaching to its fat molecules. As the dish detergent diffuses into the solution, it surrounds the fat globules in the milk. The nonpolar tails of the detergent are attracted to the fat globules, while the polar heads of the detergent interact with the water and dye molecules. The molecules of fat in the milk bend, roll, twist, and contort in all directions as the soap molecules race around to join up with the fat molecules. During all this fat molecule gymnastics, the food coloring molecules are bumped and shoved everywhere, providing an easy way to observe all this invisible activity. As the soap or detergent becomes evenly mixed with the milk, the action slows down and eventually stops. The end result of all this mixing and swirling of polar and nonpolar molecules is the tie-dye milk that we see here.